If you understood the preliminary considerations of elastic collisions, then this will hopefully make a little more sense. We are going to do the analysis of an elastic collision. And we know that, well, here is a simplifying consideration, namely, that while the collision takes place, the force of interaction between the two are proportional to separation. The way that's going to happen is that I'm going to use the example of a cart with a spring plunger. So it'd be helpful to be able to show you this directly, but as one cart hits the other cart, the spring plunger compresses, and so the force is proportional. Actually, the force is proportional to the compression. But as the compression takes place, the separation diminishes. Namely, the two carts will come closer together. So I have a force separation graph, and we start by them being separated sufficiently so that they don't even touch. So here is what I mean. There is like the path where we're going toward less separation. So I'm showing that as these arrows. We haven't touched yet. There's no interactive force. Until they hit, now they're interacting more strongly all the time. As you see, these arrows are showing how the force is increasing as the separation decreases. So with a reduction in separation, that's consistent with the plunger on the cart compressing. The center of masses of the carts are getting closer together, so their separation is reducing, force increasing. This is the minimum separation between the two objects, in this case the carts. So that's the force separation graph. Notice that the force increases linear with a reduction in the separation. Reduction in separation being the same thing as compression of the plunger. Do you got all that? Well, good. Now, on the way out, when you separate the two carts, you decrease the plunger compression. And so I'm showing that with these blue arrows, following the same path on the way out. And there you go. So that's the return path, if, say, they bounce off each other. All right, so that was a mouthful and a mindful. So now let's look at these carts and what I kind of have going here. This is still preliminary, to be honest. And so I'm showing the interaction between these two carts. I don't show the plunger yet. But the kinetic energy through a collision. One cart, M1, hits cart M2. So it initially is moving at speed v0, say, and hits this one at rest. These forces are the equal and opposite forces of one cart on the other. So this is the force of cart M2 on cart M1, and this is the force of cart 1 on M2. So it pushes on M2. Make sense? Now, during the collision, cart M1 moves a distance d1, cart M2 moves a distance d2. Now right now I'm showing them being different sizes, but for this first analysis, through a collision, they'll end up being the same distance. But in general, they can be different distances. Now let's take a look. Work done on cart 1, work done on cart 1. Well, you know the distance, displacement in particular, and the force are in opposite directions. The work done by a force is Fd cosine of theta. But the angle between F and D1 is 180. So this is minus FD1. So it's negative work. Work on cart number 2. Notice the force from cart 1 is to the right. Displacement is to the right. It's Fd2 cosine of theta. Cosine of theta is 1. So it's Fd2. So what we have is negative work, positive work. So this one lost kinetic energy, M1 lost it, while M2 gained it. The kinetic energy lost by cart 1 is just simply the negative work done. So it's work on cart 1. It's delta K1 is minus FD1. Likewise, the kinetic energy gained by cart 2 is the positive work done on cart 2. So it's work on 2, delta K2 is FD2. Now, if this collision from contact to contact, from the point that they touch each other to when they stop touching each other because they bounce off, that would be perfectly, if it's perfectly elastic, then the force we're talking about is just the same size, okay? Minus F is equal to F. Those forces are equal and opposite. Then D1, these distances in that situation, perfectly elastic, they are the same. And if that's the case, then FD1 equals FD2. And so that means that the kinetic energy lost, this one, is equal to the kinetic energy gained by the other cart. So now we're going to look at that in even more detail. And I'll try not to make this video go on too long. So let's dive into the details here. The kinetic energy during the collision. We're going to split it up into the first half and second half. And the masses are equal in this case. So masses are equal. So in the first half of the collision, we have cart number 1 coming in, and it's going to collide with cart number 2. So it's coming in at a speed of V0. There's a spring bumper here that is going to go into cart 1. There's a spring loaded, so that force is going to increase as the separation decreases. So I'm going to kind of put these markers here to denote their positions to begin with, and then M2 is going to actually move a certain distance, and so is M1. Well, in the first half, because M1 is pushing in, the spring bumper is pushing into M1, you're reducing the separation between the two. This is the minimum separation shown right here, where the center masses are as close as they're ever going to get. It starts touching here, but they still, notice, the separation gets less because the spring is compressing. So really the delta S is from here to here. This amount that the spring was compressed, the amount the plunger went in, is the change in separation. And the minimum separation is just between the two here. Technically, I should say the minimum separation is between their center masses. But in any case, this condition here is where they are closest together. And it changed by this much. So now what we see is D1, the distance that cart 1 traveled during the first half of the collision, while they're colliding. D1, but cart 2 didn't move very much. Cart 2 just moved D2, just moved a little bit in the first half. Began accelerating, but the spring plunger was pushed into cart 1. All right, so these represent negative and positive work for the reasons we've already discussed. Negative work, positive work on cart 2. So D1 is greater than D2. Simply means that the kinetic energy lost. This represents lost kinetic energy. This represents gained. So the lost is bigger than the gained. All right. The spring compresses. And really, that kinetic energy that's lost is stored in the compressed spring. This is a conservative force. Mechanical energy is maintained. Now we're ready for the second half. During the second half, these two carts are moving together momentarily at the minimum, and then as the spring plunger is shoving on this cart, pushes them apart while they continue to move to the right. Well, the way in which that happens, okay, you see cart number 1 moving a little bit in the second half, but cart number 2 actually moves a lot as it's continuing to be accelerated by this plunger pushing out. So D1 is small, D2 is quite a bit larger. The opposite of what we saw in the first half. Okay, so again, negative work and positive work. But this time, D2 is greater than D1, and therefore, the kinetic energy gained is greater than the kinetic energy lost. So these are kind of like symmetrical scenarios. Loss of kinetic energy, gain, net gain in kinetic energy in the second half. So now we can graph this. We're going to graph kinetic energy with respect to time, and I don't really care about the time so much. It's really intuitively it's like more a function of position here. In other words, what's happening to the kinetic energy? Well, the kinetic energy starts with cart 1, but then in this first half, everything that happened here, the kinetic energy reduced. But then in the second half, it came back up, and the K total afterwards is the same as the K total before. All right, now there's a certain amount of energy represented by this blue arrow. What is that? That energy, well, it's really like this dip in energy. It doesn't go away because look at it, it comes back to kinetic. So this represents the stored energy or the internal energy of the two-cart system. It's the mechanical energy internal. And in this particular case, that internal mechanical energy is stored in spring potential form. That's what it's really corresponding to. So during the collision, some of the K is converted to elastic potential energy. That's the internal energy. That internal energy is then restored back to kinetic during the second half. So is this making sense? Very good. This video will come to an end. I just want to now show you the specific amounts of energy gained and lost during the collision. So finally, just how much potential energy is stored during the collision. So here's the kinetic energy detail again, and we have that internal elastic potential energy stored during the collision. Now at the collision midpoint, we're going to consider what happens there. And again, consider that this is the case where the masses are equal. It will be different for other mass combinations. Well, at the collision midpoint, if you think about it, at the midpoint, at minimum separation, the two carts, are they going at the same speed? If you answer no to that, then the separation is changing. It's either getting greater or less. So for the separation to be minimum, they're not coming together, and they're not moving apart at that point. So they're both moving at the same speed. Well, that's good. That's like in our momentum considerations where we have an inelastic collision and they stick, at least for that brief moment. So in other words, v1 prime, the velocity of cart 1, at that collision midpoint is equal to the velocity of cart 2. So that's what the v1 prime and v2 prime is. So since they're the same, let's just call it v prime. After the midpoint, okay, at the midpoint in particular, the velocities are the same. So then, total momentum is equal to m1 v1. That was the initial momentum. That's also the final momentum, or the momentum at the midpoint. And at the midpoint, it's m1 plus m2 times this new velocity, v prime. All right, so that shows a very useful relationship. Now mv1 equals 2m. Since m1 and m2 are the same in this case, that would just be convert all the m subscripts, take all the subscripts away, just call it m. So then we have 2m v prime. Now the m's divide out, and we have v prime equals v1 over 2. So basically, at the collision midpoint, the speed is half of what it was with cart 1 to begin with. So now we're just going to look at the kinetic energies. We look at the kinetic energy in the middle, look at the kinetic energy total, relate those two, see what that relationship is, and that'll give us the answer. Well, here it is. 1/2 of, at the midpoint, it's, both carts, 2m, half of the speed squared over 1/2 m v1 squared. All right, so cancellation here. Plenty of cancellation. I like cancellations. Oh, yes. Which gives us 2 over 4 over 1, which is 1/2. So we have our answer, namely, that the ratios of those kinetic energies, the kinetic energy in the middle is half of the kinetic energy total, or 50%. And that's what I show here, too. It's the 50% point. So at this point, the total kinetic energy of the system is half what it was at the beginning, and the stored potential energy is the other half. And then that stored potential energy all gets converted back back to kinetic energy. So we're just about done with the essential concerns about elastic collisions, but I want to also look at, in the next video, we'll check out what happens when this is no longer the case, where the m's are actually different. That's kind of interesting as well. See you then.